In this video, I'm going to talk about focal length and focal point. Now, for most starting courses, we're going to talk about that. We're going to talk about spherical surfaces. For example, in a 2D view, that's a circle, and there's not actually truly one exact focal point, because if a ray comes in and it's farther from the center line than another ray, they actually, when they reflect or refract, they actually slightly have a different point where they would cross. But as long as you make the thickness of the lens really thin, and therefore its height is short relative to its radius of curvature, or the height of the mirror is really small, then that's a close approximation. But for a parabolic device, like in 2D would be y equals x squared, truly rays even at different height would either reflect or refract, and they would come to the exact same focal point, regardless of how distant they are from the center line. But we'll kind of ignore this for now, and we'll just talk only about mirrors that have short height relative to their radius of curvature, or lenses which are very thin. And then this approximation, even for spherical surfaces, is pretty good. So look at 4 different cases here, actually 5 different cases here. The first case, concave mirror, and so here's the surface of here's my mirror, and this is my reflective side is on the left, and so the surface of the mirror is my zero distance point, and I'm assuming I'm going to have rays which are coming perpendicular to this surface of that mirror, and are parallel to each other. For example, they're coming from infinity. Now they hit the surface of this mirror and they reflect off, and so there the angle of incidence equals the angle of reflection. So I find it's perpendicular to the surface at that point, right? So so they reflect off, and they reflect to this point, which is called the focal point. And for and you can see, and for a mirror, you'd expect that if I have an object on this side, I expect a real image if one exists on this side. So you can kind of see that focal point is on the side I expect for a mirror, and therefore the focal length is going to be positive. Now for a convex mirror here, again, here's the reflective side of this mirror, and here's these rays coming in. Once again, they hit this, and then angle of incidence equal angle of reflection. And here's my perpendicular, and you can kind of see that they hit here and they bounce off here, and this one hits bounce out there. But if I take that directionality and I keep projecting it back behind the mirror, you can see that they come to this point, again the focal point here, and since it's behind the mirror, the focal length is minus. And you can kind of see in both of these cases where the hit is this focal length is half the radius of curvature. So there's my center. Those are my radius of curvature of that mirror, and there's my radius, and my focal length is half the radius. There's my radius, my focal length is half the radius. But in this case, the focal length is positive because it's on the side I expect for a mirror. This time, if I project those rays, so here's the true rays, and here's a virtual ray on the back side projection of that. There's my focal point where those rays would all converge. And now for a lens, again, here's my very thin lens, and if I have rays coming here which are perpendicular to the center of the lens and parallel to each other, this time they have refraction that takes place, and because they change media. So this would, for example, air, and this might be glass or something. They refract, and they will then refract it to this point, and so that will be their focal length. And for a mirror, if you expect to see a real object on this side, a real image on that side, that may kind of make sense that this define a focal length which is positive, because for a convergent lens, they're kind of converging to this distance which is called the focal length, which is greater than 0 on the backside of the lens. Now for a divergent lens, I have these rays coming in. Again, they refract, and this time they're diverging. And so in the direction that these rays continue, they're not going to come to a point, but if I project back along where they are, that they would converge at this focal point, which is on the same side as the incoming rays, and therefore this focal length is a minus. The other case, I guess, would be, in addition to these, would be like a plane mirror. In this case, the focal length is infinity because this ray coming in, the angle of incidence is 0 because it's perpendicular to this, and so the angle of refraction is also that. So there is no point where I can find where they converge. So my focal length is infinite. Some other definitions to think about for a lens. There's a definition called power, and output power is just 1 over the focal length. And typically, remember the focal length can be plus or minus, so the power can be a plus or minus value as well. Focal lengths are typically, for example, in SI units measured in meters, and power is 1 over meters, and the units for that is diopters. So if you go to ophthalmologist, he'll talk about a power of a lens, and he'll talk about units of diopters, which is essentially just meters to the -1. One other thing about lenses, lenses don't have to have the same spherical, or the same curvatures on one side or the other. Actually, so here I've drawn one that's curved this way, and then the other side is just flat. And what it turns out is, if I have these rays which are coming in, perpendicular to this center line of the lens, they will refract. Draw it a little better. They would refract and go through this focal point, as we talked about before. And so here's the focal point is for rays coming in from the left side, and it being converged in this case to this focal length seen on the right side. Now it turns out that if I had rays coming from the other side, parallel rays, and they refracted, they would also go to the point on the opposite side, and the focal length on the right would be the same as focal length on the left. And that's true whether it's a convergent one as shown like here, or a divergent one is shown. So if I could have a divergent and a flat, I would have focal lengths being negative, being the same magnitude right or left.